complete teach you about it in this my video. But first of all, if you are new, so also please subscribe my channel, press the bell icon so you start my topic and discuss about it, electrical conductor. So now you start. In physics and electrical engineering, a conductor is an object or type of material that allows the flow of charge, electric current in one or more directions. Material made of metals are common electrical conductors. The flow of negatively charged electrons generates electric current. Positively charged holes and positive or negative ions in some cases in order to current and to flow within the closed electrical circuit. One charged particle does not need to travel from the component of producing the current. The current source to those consume it. The loads if the charged particle simply needs to nudge its neighbor feed it among who will nudge its neighbor and on until the particle is knocked onto a consumer, thus powering it. And essentially what is occurring is the long chain of momentum transfer between mobile charge carriers. The root model of conduction describes this process more rigorously. The momentum transfer model makes metal in ideal choice for a conductor. Metals typically possesses delocalized sea of electrons, which gives the electrons enough mobility to collide and thus effect a momentum transfer. And discuss about electrons are the primary movers in matter. However, other devices such as the cationic electrolysis S of a battery or the mobile protons of the proton conductor of a fuel cell rely on positive charge carriers, insulators or non-conducting materials with few mobile charge that spot only insignificant electric currents. And resistance and conductance. The resistance of a given conductor depends on the material that is made of and on its dimensions. For a given material, the resistance is inversely proportional to a cross-sectional area. For example, thick copper wire has lower resistance than an otherwise identical thin copper wire. Also, for a given material, the resistance is proportional to the length. For example, long copper wire has higher resistance than an otherwise identical short copper wire. The resistance R and conductance G of a conductor of uniform cross section therefore can be computed. R is equal P L by A, G is equal ohm A by L, where L is the length of the conductor measured in meters. M is a cross sectional area of the conductor measured in square meter. M squared. Ohm sigma is the electrical conductivity measured in Siemens per meter. Sm -1. And PRHO is the electrical resistivity, also called specific electrical resistance of material measured in ohm meters. And the resistivity and conductivity are proportionality constants and therefore depends only on the material the wire is made of, not the geometry of the wire. Resistivity and conductivity are reciprocals. P is equal 1 by ohm. Resistivity is a measure of the material's ability to oppose electric current. And this formula is not exact. It assumes the current density is totally uniform in the conductor, which is not always true. And in practical situation, however, this formula still provides a good approximation for long thin conductors such as wires. And in the situation, this formula is not exact for his with alternating current AC, because the skin effect inhibits current flow near the current of the conductor. Then the geometrical cross section is different from the effective cross section in which current actually flows. so that resistance is higher than expected. Similarly, two conductors are near each other carrying AC current. Their resistance is increased due to proximity effect at commercial power frequency. These effects are significant for large conductors carrying large currents, such as bus bars in an electrical substation or large power cables carrying more than a few hundred amperes. Aside from the geometry of a wire, temperature also has a significant effect on the efficiency of the conductor. Temperature affects conductors in two main ways. The first is that materials may expand under the application of heat among the materials. Temperature affects conductor in two main ways. The first is that materials may expand under the application of heat. The amount that the material will expand is governed by the thermal expansion coefficient specific to the material, such an expansion or contraction will change the geometry of the conductor and therefore its characteristics. However, this effect is generally small, on the order of 10 -6. An increase in temperature will also increase the number of phonons generated within the material. A phonon is essentially a lattice vibration, or rather a small harmonic kinetic movement of the atoms of the material, much like the shaking of a pinball machine. Phonons disrupt the path of the electrons, causing them to scatter. The electron scattering decrease the number of electron collisions and therefore will decrease the total amount of current transferred. That is conductor materials. Conductor materials include metal electrolytes and superconductors, semiconductor and plasmas, and some non-metallic conductors such as graphite and conductive polymers. Copper has a high conductivity annealed. Copper is the international standard to which all other electrical conductors are compared. The international annealed copper standard conductivity is 58 ms by m, and also ultra pure copper can slightly exceed 101%. And IACS, the main grade of copper used for electrical applications such as building wire, motor windings and cables and bus bars, is electrolytic top pitch ETP copper CW004A or AFTM designation of C100140. If high conductivity copper must be welded or brazed or used in the reducing atmosphere, then oxygen free high conductivity copper CW08A or AFTM designation of C10 and 1000 and may be used because of its ease of connection of soldering or clamping. Copper is still the most common choice for most light gauge wires. Silver is 6% more conductive than copper, but due to the cost, it is not practical in most cases. However, it is used to specialized equipment such as satellites and as a thin plating. To mitigate skin effect and losses at high frequencies. Famously 14,700 short tons 13,300 T of silver on loan from the United States Treasury were used in the making of a Calutron magnets during World War II due to wartime shortage of copper. Aluminium wire is the most common metal in electric power transmission and distribution. Also, only 61% of the conductivity of copper by cross-sectional area. Its lower density makes it twice as conductive by mass as aluminium. Is roughly 1/3 the cost of copper by weight. The electronomic advantages are considerable when large conductors are required. The disadvantage of aluminium wiring lie in its mechanical and chemical properties. It readily forms an insulating oxide, making connections heat up its large coefficient of thermal expansion. Then the brass material used for conductors causes connections to loosen. Aluminium can also creep slowly and deforming under load, which also loosens connections. These effects can be mitigated with the suitably designed conductor and extra care in installation, but they have made aluminium building very unpopular past the service drop. Organic compounds such as octane, which has 8 carbon atoms and 18 hydrogen atoms, cannot conduct electricity. Also are hydrocarbons, since carbon has the property of tetracovalency and forms covalent bonds with other elements such as hydrogen. Since it does not lose or gain electrons, thus does not form ions, covalent bonds are simply the sharing of electrons, and hence there is no separation of ions when electricity is passed through it. Liquids made of compounds with only covalent bonds cannot conduct electricity. Certain organic ionic liquid, by contrast, can conduct an electric current, and while pure water is not an electrical conductor, even a small portion of ionic purities such as salt can rapidly transform it into a conductor. And in wire size, wires are measured by their cross-sectional area. In many countries, the size is expressed in square millimeters. In North America, conductors are measured by American wire gauge for smaller ones and circular mills for larger ones. And conductor ampacity, the ampacity of a conductor, that is the amount of current it can carry, is related to its electrical resistance. Lower resistance conductor can carry a large value of current. The resistance in turn is determined by a material the conductor is made from, as described above, and the conductor size for a given material. Conductor with a large cross-sectional area have less resistance than conductor with a smaller cross-sectional area. For bar conductors, the ultimate limit is the point at which power lost to resistance causes the conductor to melt aside from for fuses. Most conductors in the real world are operated are below this limit. However, for example, household wiring is usually insulated with PVC insulation that is only rated operated about 60 degrees C. Therefore, the current in such wires must be limited so that it never hits the copper conductor above 60 degrees C, causing a risk of fire. And other more expensive insulation such as Teflon or fiberglass may allow operation at much higher temperatures. And anisotropy, in an electric field is applied to a material and the resulting induced electric current is in the same direction. The material is said to be an isotropic electrical conductor. In the resulting electric current is in a different direction from the applied electric field. The material is said to be an anisotropic electrical conductor. So my dear friends, how is my topic? I hope you like. So now you give me permission, I am going to my new web topics. Take care and Allah Hafiz.